Alright, so today we're starting with Chapter 7. Depending on whether you're taking A, B, or BC, BC goes all the way through Chapter 7, includes all the sections, and AB only goes through Section 3. So you're not going to have as many videos and not as many sections of homework from Chapter 7 if you're in AB. But whichever group, we all have 7-1, so let's go ahead and get started with this. Alright, for instance, let's say a honeybee makes several trips to the hive, from the hive to a flower garden. The velocity graph is shown below. So this is his velocity graph. Well, if we go in here and we calculate, we can find out what the total distance is traveled by the bee. Well, here he was flying for 100 feet per minute for 2 minutes. That means he covered 200 feet. Down here, from minute 3 to minute 4, he did the same thing. And from 6 to 8, he did the same thing. And then from 9 to 10, he flew at 200 feet per minute, but only flew for 1 minute. So he only flew 100 feet. So if we wanted the total distance that traveled by the bee, notice here we've got positive velocity. Here we have negative velocity, positive velocity, negative velocity. So in other words, he's traveling away from the hive here, back to the hive over this interval, away from the hive here, and then back toward the hive here. So what's the total distance traveled by the bee? Well, 200 plus this 200 plus this 200 plus that 100 gives us 700 feet that the bee traveled. That's the total distance traveled. So that means how far, essentially how many steps did this bee take, regardless of what direction it was in. Right, so that's one way that you're going to have questions asked like this. What's the total distance traveled? You need to make sure that you understand that versus the next question we're going to ask. What is the displacement of the bee after 10 minutes? In other words, what's the location of the bee after the 10 minutes? So if we go through and do the exact same thing again, we go 200 feet away from the hive, negative 200 feet back to the hive, 200 feet away from the hive again, and then negative 100 feet back from the hive. Where is the bee going to be at that moment, at that 10-minute mark? Well, the bee is going to be 100 feet away from the hive. Now, the hive is essentially what we're taking as our origin. Now, all of our displacement and velocity and everything is going to be in linear motion. It's going to go along a line. So we're imagining that bee is going straight out to the flower, straight back, straight out to the flower, and then halfway back. So it's 100 feet to the positive from the hive. Now the reason we say to the positive is because if the bee had gone 200 feet this way and then 300 feet this way, it would be negative 100, so it would be on the negative side, would be his final location. So it's important to denote those signs when we're talking about any of these things, but really important when it talks about displacement. When we're talking about total distance, we essentially take the absolute value of everything and add them up. But when we're talking about displacement, we've got to wonder and keep in mind what the sign of each part is. So 100 feet towards the hive is where the bee is and where he's going. He's at 100 feet from the hive, but he's headed towards the hive. Now, to find the displacement or the position shift from a velocity function, we just integrate the function. That will give you the final position with all the positives added in and all the negatives added in and all that. Now, the negative areas below the x-axis subtract from the total displacement. Anything below the x-axis is going in the opposite direction of anything above the x-axis. So they cancel each other out as much as possible, and we actually get the true displacement. So the displacement is just the integral from A to B of v of t dt, where A is the starting time, B is the ending time. Now, to find the distance traveled, we have to use the absolute value, because anything that's negative we actually want to take and make positive because it's distance traveled too. Here's what I want you to think about. I want you to think about me going out on a hike. Well, let's say I start here and I walk 5 miles, and then I turn around and I walk 5 miles back. Well, the difference between these two things, displacement and distance traveled, you need to think about what you want credit for. I'm a big guy. I'm fat. So if I walk 5 miles out and then walk 5 miles back, I want credit for 10 miles walked. Now, if it's not that big a deal for you to get out and walk 5 miles or even run 5 miles, then all you're really worried about is that you end up back home. So your displacement would be 0. So that's the difference in these two. Distance traveled, you're counting every single possible step, mile, foot, whatever you want to do, no matter what direction it's traveled. That's why you do the absolute value. So any negative 5 miles out, negative 5 miles back is counted together. If you take the absolute value and you add this plus that, you get 10. Here there is no absolute value, so you add the 5 miles and you add the negative 5 and you get 0. So that's the difference between these two. All right, now if you have to do a distance traveled one where you're doing the absolute value by hand, what you're going to do is you're going to find the roots or the zeros of the velocity equation. In other words, find where it's crossing the x-axis over the time interval you're dealing with, and integrate it in pieces, just like when we found the area between a curve and the x-axis. In other words, you're going to take the absolute value of each integral. Or you can just use your calculator to integrate the absolute value of the velocity function. You can do absolute value. It is in the catalog, but so you've got to actually put that inside your integral. Don't do the absolute value after the fact. You want to do the absolute value inside the integral on your calculator, so it's taking the absolute value as it goes along and adds all the parts up. Now, we're going to look at one of these here in just a second. So if that doesn't quite make sense, it'll make a little more sense when we see an example. All right, so the velocity graph here, the displacement, we would find how much was traveled here, how much was traveled here, this being positive, this being negative because my y value is negative. And then I would add those together. So you can calculate that by finding there's a couple ways. You could do the trapezoid thing, or you could split it right here and make a square of 1 and a triangle of 1/2. You could do the same thing here. There's your triangle of 1/2 and 2 squares of 1. So we end up with 1.5 plus negative 2.5. So our displacement is going to be at a location of negative 1. Now, what if we wanted to find the total distance traveled? Well, in that case, everything down here that's negative we would actually think of as being positive. So we would have 1.5 plus 2.5. And that would give us 4. Now, this may help you understand this a little bit. So if we were doing an integral, let's say we couldn't find the easy things, but we had the equation of this graph. What you would do here is you would integrate from 0 to 2 of your function. Now let's do it with respect to t. Now, why do we choose to go from 0 to 2? Well, 0, of course, is the starting point. 2 is our 0. That's where it transitions from being a positive valued function to a negative valued function. So if we wanted to find, let's say, the displacement, nope, hold on. Let me write that over here. Let's do the displacement. Would just simply be, there is no absolute value thing, so all you would do is be the integral from 0 to 5 of f of t dt. Now, if you wanted the distance traveled, we have to take and make this down here positive. So if we're doing it by hand, this is what we have to do. We have to split it up into 0 to the first 0, literally 0 to the 0 of the function is what I mean. And then from that 0 of the function to either where it ends or where it has another 0. So we would add the integral from 2 to 5 of f of t dt. Now, I want you to think for just a second, is this going to work for what we've got, what we have right here, looking at this graph? If we integrate from 0 to 2 of f of t dt, I'm going to come up with a positive number because all this is positive area above the x-axis. Now, if I integrate from 2 to 5 over here, I'm going to end up with a big negative number. So this is going to be a negative, and that's not going to work because I wanted absolute value. So what would you do? Well, you could go out and you could change this thing right here to a minus, and you subtract every interval below the x-axis, and that's going to make that into a positive. So now we're going to end up adding two positive values, and that's going to give us the total distance traveled. So that's how you would go about doing it. And that's what we were talking about on the last slide, is how you break it up. You would have to break it up into integrals of above to the 0 and below to the next 0. And what I mean there is if this thing had come back up and gone here, and we're going to 6, you would go from 2 to 5, just like we did here, but then you have to go from 5 to 6 back above. So you may have those that have more than one 0 there, but that's how you split it up. Anything that's going to give you area above the x-axis is a plus. Anything that's going to give you negative area, which is below the x-axis, you're going to subtract. But that's only when you're looking for the total distance traveled, because you don't want this to take into account the fact that it's going backwards. You want to count all the distance. All right, and then if this is the velocity graph, this is actually the position graph. Here we have moving away from the position in the positive direction. And from 0 to 1, notice it's moving in a constant velocity, so we've got a constant slope here. Then it starts getting less, the velocity does, which means that the slope of the position function is going to get less. At 2, it has a maximum value. That's the furthest away it's going to go. And then it travels in the negative direction. So that means it's going to be coming back down. Remember, this is position. This is not velocity or anything. It's actually the position. So it got a maximum position of about 1.5 feet or inches or whatever unit we're using here. And then it starts moving back to 0. So it started moving back to 0. And then here at 3, it started moving at a constant velocity. So the slope's constant all the way to 5. Now at 4, what happened? Well, at 4, if you think about what happened right here, if it moved 1.5 feet, inches, whatever away here, then it moved back 1.5 and a foot. Then at that point right there, 4, it did what? It got back to where it started from. and then it continued moving in that same negative direction for another minute, whatever this unit of time is, and that's where you get this part. And this right here is a value of -1, which is, guess what? What we got right there. That's the displacement. That's where it ended up. Now, note here, and this is true, this was true when this guy put this thing together, and this is true with all the years that I've used this slideshow. Every AP exam I've seen has had at least one problem requiring students to interpret velocity and position graphs. You have to be able to read back and forth and tell you what this thing means. And you may even have to go from here and figure out what this thing kind of looks like, or the other way around. So remember, the velocity graph is nothing more than the slope of the position graph. So you can plot those slopes at any time. In the same case, if you have the velocity graph and you know where it starts, then you can use this as slope. Start off at a point, and use this as the slope to kind of build your graph here. All right, in the linear motion equation, ds dt equals v of t. That's the derivative of the position function with respect to time is velocity. If we multiply both sides by dt and then integrate, we're going to find hang on, this is going a little deeper than I thought. All right, so for a very small change in time, v of t can be considered a constant. The velocity is not going to change at a very small instant of time. If we add up all the small changes in s to get the total distance, that's what this is right here. So change in s is v of t delta t, and s, the whole position, is just all this. Well, the delta t, we're taking even terms so we can factor that out. And that gives us the integral, or the sum, as n goes from 1 to k of v of n delta t. Remember, that's your change in time. This is your velocity at that moment in time. And this is just saying that you have n intervals that or n values of v that you're going to add up. Now, if we change and don't go to k, but we go to infinity, letting an infinite number of velocities being taken at that time, well, then this becomes nothing more than an integral. So s is nothing more than the integral of v of t dt. Okay, a summation notation, this is a finite number. K might be 2, it might be 7 million, whatever, but there's a finite number of terms that you can add up. If you go from n equaling 1 to infinity, this is actually now becoming something where delta t is infinitely small, so this becomes integration. Now, the same type of unit same kind of deal we can use in real life situations. Let's say the potato consumption for a particular country was C of t is equal to 2.2 plus 1.1 t. This is a base level, and this is the growth level, where t is the number of years since 1970, and C is in millions of bushels per year. So for a small delta t, the rate of consumption is constant. The amount consumed during that short time is C of t times delta t. So you find the C of t value, multiply it by that little small change in time, and you can figure out how much you're actually this country is consuming over that small moment in time. Now, if we add up all these small amounts to get the total consumption, we end up getting the integral C of t dt. That's the total consumption over the years of the integral. So, from the beginning of 1972 to the end of 1973, now remember, this thing said that the t was based on 1970 being 0. So the beginning of 1972 is 2. The end of 1973 is when 74 started, so it'd be 4. So that's why we're integrating from 2 to 4. And this is nothing more than c of t dt. So when we integrate this, we're going to get 2.2t plus 1 over the natural log of 1.1 times 1.1t. Now if you forgot where that came from, remember we had our rule that said we had the derivative with respect to x of a to the u equals a to the u times the natural log of a, where that's a constant, times u prime. Well, in this case, our a is 1.1. That works for every exponential. Except here we're integrating, so we're going to go backwards. Now, t has a derivative of 1, so we could essentially say that this is x. And that would be a to the x, and this u prime would be 1. So instead of taking the derivative, though, we're taking the integral, and the natural log of a, in this case the natural log of 1, is just a constant, so we divide by it instead of multiplying by it. That's where that comes from. All right, and then if we integrate, or sorry, if we evaluate it from 2 to 4, we're going to plug in 4, find the value, subtract when we plug in 2, and that would be our value. And if we do that, we're going to get approximately 7.066 million bushels. Now, that would probably be a calculator problem because of the natural log of 1.1 and the 1.1 of the t power and the 2.2 times t and all that stuff. So there might probably not be a non-calculator question there. All right, work. If we calculate work, if the force is constant, it's just force times distance. If you're using the exact same amount of force for the entire distance that you do the work, then work is easy to calculate. Now, when the force that you're using varies, we get to use calculus. So for instance, Hooke's law of springs is the force is equal to k times x. Where x is the distance, the spring is extended beyond its natural length. And k is some kind of is the spring constant. It'll be true for that spring. All right, so it takes 10 newtons to stretch a spring 2 meters beyond its natural length. So 10, the amount of force, equals k times 2. So that means we can solve for k, and k is going to be 5. So our force equation for this, now this is varying force, if you were to pull that to, if you were to stretch that to 3 meters beyond its natural length, you would have to exert a force of 15 newtons. Now the thing is, what do we know? We're having to put 5 more newtons for every meter more we strengthen it, or we lengthen it. So that's the deal. It's going to get tougher the more we stretch it. Well, that means what happens between the 2 meters and the 3 meters? Was it 10, 10, 10, 10, then just magically at 3 jump to 15? No, it varies all the way in between there. That's what we mean by a variable force. The further you stretch it, the more resistance it's going to give you. So that gives us, this gives us our equation of the force equaling 5 times x. So for any moment, or for any amount of length, we can find the amount of force it takes to stretch it to that far. If we wanted to know how much force it would take to stretch it 4 meters beyond its natural length, it'd be 20 newtons. But the thing is, it's not necessarily, it is not a constant force. It's a constant force for every meter, yes, but it's not a constant force. You got to understand, it took you 5 newtons to get it to hold it at 1 meter past its natural length. it takes 10 newtons to hold it at 2 newtons. So you're exerting more force the further you pull it. So when we add all those things up, let's find out how much work is done. Work and force are two different things. Remember, work is force over distance. So how much work is done stretching the spring to 4 meters beyond its natural length? Well, for a very small change in x, the force is constant. This is not that big a deal. Just remember that work is the integral from 0 to 4 in this case of the force times the distance. And we're integrating from 0 to 4. So that means we're going to end up with 5/2 x squared evaluated from 0 to 4. When we plug in the 4, we're going to get 5/2 of 16, which is going to give us 40. When we plug in 0, of course, we're going to get 0. So the amount of work done is 40 Newton meters, which is 40 joules. Right, and that's the end of 7.1. 7.1 is just taking those integrals that we've learned so far on how to do from chapter 6 and even back to approximating back to chapter 5 and apply them for actual real world examples. That's what 7.1 gets us into. When we get into 7.2, we're going to start doing more with the area under the curve or between two curves and things like that. And then 7.3 we'll get into volume.